Alright, welcome to Math 40. This is a lecture video for Monday of week 8, and I want to begin today by talking about the discussion assignment, discussion assignment number 2. I actually received quite a few questions regarding this assignment. In particular, I think the main issue was drawing the diagram. So I won't give you the complete diagram to the problem because I don't want to give too much away. But I do want to go over instructions with you and maybe have a start at the diagram. Okay, so here is the background information they gave us. A sunny summer morning, a fighter jet pilot experiences a hair-raising situation. While on a training exercise, she is alerted by the command center that an unidentified flying object has entered the airspace and will soon appear on her radar. Some moments later, the jet's radar detects the object a few hundred feet above, moving at otherworldly speeds on a bearing of 60 degrees 10 minutes. This is relative to the jet. In a few milliseconds, the object travels 8.61 miles in a straight line away from the fighter jet. At this point, radars at both the command center and fighter jet begin to mysteriously malfunction. The only data command center is able to collect is that the object has changed bearing and has traveled 5.21 miles again in a straight line before disappearing. The jet's radar is able to additionally relay that the last detectable location of the UFO relative to the fighter jet was some distance directly east of the fighter jet. Everyone is dismayed at the idea that the UFO could be flying undetectable next to the fighter jet, and so they quickly turn to you and your colleague for help, both of who are analysts and trig whizzes. Okay, so the first thing that we should try to do is take the initial data, initial position of the jet and the UFO. Okay, so let's just say that this point here represents my jet. Okay, and that's the point at which the jet first detects the UFO. Now, what do they tell us about when they first detect the UFO? Well, it says that the jet detects it moving on a bearing of 60 degrees 10 minutes relative to the jet. So what that means is that if we were to draw the four directions relative to the jet, so let's say this is north direction, east, west, and south, the UFO is traveling on a bearing of 60 degrees 10 minutes. Now remember, whenever they don't specify the initial and the initial direction and the direction in which it is moving, that means that we start at north and move towards east. So starting at north, moving towards east 60 degrees 10 minutes, we'll approximate it to be somewhere here. Okay, so the UFO is traveling somewhere in that direction. Okay, now what else do they tell us? Well, they tell us that at this point, after it's detected that it's traveling, oh, and by the way, they also tell us how far it traveled for. It traveled for 8.61 miles in a straight line. Okay, so this distance is 8.61 miles to the location of the UFO. Okay. Then what? After that last detection, the radars begin to malfunction, and the only thing that they're able to determine is that the UFO has changed direction and has traveled again, and it has reappeared. So okay, the only data they're able to collect is that it changed. It has changed bearing, meaning it has changed direction, and has traveled 5.21 miles again before disappearing. So we don't know how it rotated here at this point, right? All we know is that it changed direction and it's 5.21 miles away from this point. They do tell us though that they are able to later pick up that the last detectable location of the UFO relative to the fighter jet was some distance directly east of the fighter jet. Okay, so directly east means along this direction. So somewhere along this line, okay, was the last detectable location of the UFO. So even though we don't know what the change in bearing was, eventually we are going to be able to find it because we know that it traveled in this direction for 5.21 miles. Okay, it was only while it was traveling in this direction that we couldn't really tell how it had rotated. But later on we did find that it was directly east relative to the jet. Okay, so what we need to determine is whether or not this triangle is possible, or if maybe there is more than one possible triangle that has these distances and that has this initial angle 60 degrees 10 minutes. Okay, so that's for you guys to determine and answer on the discussion forum. Okay, so continuing on with the lecture notes, I want to make a quick announcement. So last week I posted up a set called Lecture Notes Week 7 and 8, and this is page 9 on that, this would have been page 9 on that set of lecture notes. But since then there have been 2 changes. So I've actually uploaded a new set called Week 7, and everything that was part of 7 and 8 is now just labeled week 7. The second thing that changed is that on page 9 there was a typo. These values had a negative 1.41 and a positive 1.41 rather than 0. So if you have a version of the lecture notes that has a 1 here instead of a 0, go ahead and cross that off. Because it was a typo and it should be a 0. Okay, so let's continue then. On page 9, we're taking a look at how to graph the tangent function. So we've been given a list of x values, and we've also been given the corresponding y values already in the form of a point x comma y. So really the only thing that is missing is the work in showing that the y value is indeed what is already listed here. And so that's what we're going to do for this part of the table. So the first x value is negative pi over 2. And we can actually find negative pi over 2 on our unit circle. If you take a look at the unit circle, negative pi over 2 is going to be an angle that opens clockwise, and it's going to open 90 degrees because if you recall, pi over 2 is the same as 90 degrees, but in the clockwise direction is how we get the negative part of it. So that corresponds to a coterminal angle of 3 pi over 2, and the point that's associated to it is 0, negative 1. Now, if you remember from the second definition that we learned for the trig functions, tangent is defined to be y over x. So if we want to find out what is tangent of negative pi over 2, we need to take the y value of the point, which is negative 1, divided by the x value of the point, which is 0. And so we're going to get undefined. Yeah, we're going to get undefined in this case. So tangent of negative pi over 2 is undefined. And that always corresponds to an asymptote, already listed here. Okay, now let's take a look at negative 3 pi over 8. Negative 3 pi over 8 is not something we have on the unit circle. So what we're going to do is we're going to rely on our calculator for that. Make sure that you are in radian mode before you proceed to enter that. So we'll have tangent of negative 3 pi over 8. That gives us approximately negative 2.4142. Okay, which is this y value. If we take a look at the next one, tangent of negative pi over 4, that one you have the option to use the unit circle to help you find, since pi over 4 is on the unit circle. But just because we've already have our calculator in our hands, let me go ahead and punch it in. Tangent of negative pi over 4 is negative 1. So that agrees with the y value there. And we'll do a couple more. We'll take care of these two, and then for the rest of them, we'll trust that these y values are correct. But we'll have tangent of negative pi over 8 gives us negative 0.4142 approximately, which is that y value given. Okay, and we'll do one more. Tangent of 0. Again, 0 is something that's on the unit circle, so you can use it to help you find the y value. But if we punch it in, we get tan of 0 is 0. So that's how we're getting that point. Okay, so for the remainder of the x values, I encourage you to use your calculator to help you verify that these numbers and points are correct. I'm just going to write tan of pi over 8. You want to verify that that's going to give you approximately 0.4142. Tangent of pi over 4. Use unit circle or calculator to help you verify that it gives you y value of 1. Tangent of 3 pi over 8. Verify that it will be approximately 2.4142. And the last one, just verify that tangent of pi over 2, which you can use your unit circle to help you, is going to give you undefined, and therefore will be an asymptote on the actual graph. Before I actually plot the points, I want to consider what x values I need to be able to identify on the x-axis. So what I mean by that is, look at these x values. We need to make sure that we know where is pi over 8, where is 3 pi over 8, where is negative pi over 8, and negative 3 pi over 8. Yeah, so to be able to identify where that is, let's just think about where is pi over 4. Because if you consider what is half of pi over 4, half of pi over 4 is pi over 8. So that means that halfway between 0 and pi over 4, we'll find pi over 8. So where is pi over 4? Well, pi over 4 is half of pi over 2. So if I take half of pi over 2, that is pi over 4. So this would be halfway between 0 and pi over 2. And we said half of that is pi over 4. And then halfway, or half of pi over 4, so halfway between 0 and pi over 4, that's pi over 8. So this is allegedly right in the middle. Okay. So this is like 1 pi over 8. This would be like 2 pi over 8, which reduces down to a pi over 4. This here would be a 3 pi over 8 then. And this last tick mark would have to be 4 pi over 8, which agrees because if you reduce that, it gives you a pi over 2. Okay, so we're able to label these tick marks and get multiples of pi over 8. Now if we go into the negative direction, halfway between 0 and negative pi over 2 would be negative pi over 4. And then halfway between 0 and negative pi over 4, we would get this negative pi over 8. So now again, it's just a matter of counting. This is negative 1 pi over 8, negative 2 pi over 8. Halfway would be negative 3 pi over 8, which I'll go ahead and draw up here so that it doesn't interfere with the next labeled tick mark. And then the last one would have to be a negative 4 pi over 8, which if you guys notice, it agrees because when you reduce, it gives you the negative pi over 2. Okay, so now that we've labeled the necessary tick marks, I'll erase these extra markings that we wrote down just to help us verify our work, and let's get to plotting the points. So the first one is negative pi over 2 with the y value of asymptote. So it's actually an asymptote. That is not a point. It is going to be this vertical line at negative pi over 2. Then at negative 3 pi over 8, that corresponds with a negative 2.41. So negative 3 pi over 8, this is negative 2, this here would be negative 3, then we would have a negative 2.5. So if I want to get negative 2.4, it's going to be right above that negative 2.5 line. Okay. Then negative pi over 4 comma negative 1. So here's negative 1. That means we'll get that point. Negative pi over 8 comma negative 0.4. Again, this is negative 0.5. So negative 0.4 is going to be right above it. So it's actually going to go into our label there. Then we have 0 comma 0, 0.8 comma 0.4. So I'm just going to label these in really quick. Okay, this would be this would be positive 0.5. Actually, it's a little bit higher, halfway. So 0.4 is going to be right beneath that line. Then at pi over 4, we reach 1. At 3 pi over 8, we reach 2.4. So here is 2.5. That means that 2.4 will be right below that line. And finally, at pi over 2, we have undefined again, which means we have this vertical asymptote. Okay, so what does this mean for tangent? For tangent, we're going to have a curvy line, or I should just say a curve, that will go down to negative infinity if we try to get to negative pi over 2 from the right-hand side of the x-axis. Okay, so this is just going to continue to go down. And then we're going to pass through these points, and then it's going to shoot up to positive infinity. And the way that we know that is because we have an asymptote, but you can always go in and double check. You can always try to get a value that's really close to pi over 2, but still less than pi over 2, and plug it into tangent. So let's see, like if I do pi over 2, that is 1.5707. So if I tried tangent of, say, 1.56, that gives me 92. If I try to get closer to 1.5707, I can do tangent of 1.5700, and that's going to give us 1,255. So you can see that the closer I get to pi over 2, the higher and higher the number is going to get. Similar behavior is going to happen if you try to get to negative pi over 2. Okay, but this is what one cycle of tangent is going to look like. If we extend the graph beyond pi over 2, so beyond pi over 2, we're going to see this part of the graph repeat. So let me actually just use some highlighters here. So this bottom part of the curve that goes into the negatives and gets really close to the vertical asymptote starts repeating here between negative pi over 2 and pi. And then this part of the curve, which is positive and curves up towards the asymptote at pi over 2, repeats at between pi and 3 pi over 2. So altogether, this whole thing, this curve that's connected between negative pi over 2 and pi over 2, repeats between pi over 2 and 3 pi over 2. Yeah. Same if we go more in the negative direction, we'll see that that part of the curve is going to repeat between negative 3 pi over 2 and pi over 2. So just to make sure that it's very clear to us, this is one whole curve that is repeating in those areas, in these intervals. We're going to be using that to help us find the characteristics of tan of x. So what is the domain? Do we have any restrictions of x values that we cannot plug into the tan function? Well, we do have some x values that cause issues, specifically those where we get an undefined answer for tangent. Those happen wherever we have the asymptote. So if you notice, it happens at negative 3 pi over 2, at negative pi over 2, at pi over 2, basically at any odd multiple of pi over 2. So what we can write here is the domain is all real numbers. So from negative infinity to positive infinity, except the places where x is equal to an odd number. And if you remember, an odd number can be represented with 2n plus 1 times pi over 2, where n is representing any integer 0, plus or minus 1, plus or minus 2, so on and so forth. And so that's for the domain. For the range, that is asking what are all the possible y values that you're going to obtain from tangent. Well, from tangent, there is no restriction on y values, right? If I'm gonna, no matter how far negative I get, there will be a part of the graph that touches that negative y value. So I can always look back and see what is the x value that corresponds to the very negative y value that I chose to consider. Same thing if I go up in the positive direction, it doesn't matter how far up I go, I'm still going to be able to find an x value that corresponds to whatever positive y value I'm considering. So the range doesn't have any restriction. It goes from negative infinity to positive infinity. Okay, and then what about the amplitude? Well, if you recall, the amplitude was half the distance between the highest y value or the largest y value and the smallest y value. In this case, the largest y value, so let me just write that, y max, doesn't exist, right? Because it actually goes on to infinity. So this one doesn't exist. And same thing for the y minimum. There is no minimum y value because the graph extends down to negative infinity. So that means that the amplitude here doesn't exist. So we're just going to write NA. Okay, it does not apply, not applicable. What about the period? Well, the period, if you recall, is how long does it take the graph to repeat? Well, I see one unique part of the curve between negative pi over 2 and pi over 2. right? Nothing in the graph there repeats. Everything is unique. It's not until I start considering beyond pi over 2 that I see this yellow highlighted part of the graph repeat. So the period has to be the distance between negative pi over 2 and pi over 2. Okay, so that's what I'm going to write there. The period will be the distance between negative pi over 2 and pi over 2, which means that I'm going to take pi over 2 and subtract away from it negative pi over 2. Okay, this here is the period. And that is going to give us a pi over 2 plus pi over 2, which is going to be pi. And that is very different to what we got with sine and cosine. With sine and cosine, we actually got a period of 2 pi. All right, what about zeros? Where does the graph touch the x-axis? Well, it happens at negative pi, at 0, at pi, at 2 pi. So basically, at any point where we have x is equal to an integer multiple of pi, that's where we will see tangent touch the x-axis. Okay, so this is for n being 0, plus or minus 1, plus or minus 2, or anything greater. And finally, the asymptotes. Where do we have asymptotes? Well, whatever we excluded from the domain, we excluded because we got undefined, and that always corresponds to the asymptotes. So the asymptotes are going to be given by this equation here, and by x equals an odd multiple, so that's 2n plus 1, times pi over 2, where n can be 0, plus or minus 1, plus or minus 2, so on and so forth. So next we are going to consider the cotangent graph. And just like with the tan graph, they've already provided for us the x values they want us to plug into cotangent and the expected y values. So we're just going to verify maybe the first half of them, and then the rest we're going to trust that what they gave us is correct. Okay, but you can always go in and verify by either using unit circle when appropriate or the calculator for any other time. Okay, so for cotangent of 0, since 0 is an angle on the unit circle, I can take a look at what happens at that point. Okay, so this is a 0 angle. Its terminal side did not open, terminal side did not open, so it stayed where the initial side is at. In that case, we're going to get that cotangent of 0 radians is going to be x over y, because remember, cotangent is the reciprocal of tan, and tan is defined to be y over x. So cotangent will be x over y, and if you look at what are the values of x and y, we get an x value of 1 and a y value of 0. So this is going to be undefined. Okay, so here we're going to get, I'm going to write it down, this is a 1 over 0, which is undefined. And that corresponds to asymptote. What about cotangent of pi over 8? Well, pi over 8 is not something we have on unit circle, so we're going to have to use our calculator. And to do so, we can type a 1 over tangent, because remember, cotangent is reciprocal of tan. So 1 over tangent of pi over 8. And that's going to be approximately a 2.4142, which agrees with the y value that they gave us. So it's approximately 2.4142. Okay, again, let's check pi over 4. There are two options for checking pi over 4, unit circle or calculator. In this case, I'll rely on the calculator. We're going to get a 1 So that agrees with a point of pi over 4 comma 1. Let's try 3 pi over 8. Okay, that's approximately 0.4142. Okay, so that's correct. And we'll check one last one, pi over 2. Okay, so this one we want to be careful about, because notice what's going to happen if I try to plug it into my calculator. I'm going to get a domain error, which might lead me to believe like, hey, I have an asymptote here. But that's not actually the case, and here's why. Look at the unit circle. Okay, we're considering angle pi over 2, which means that we're looking here at an angle that is 90 degrees. At an angle that is 90 degrees, or pi over 2, we have the point 0, 1. So that means that cotangent of pi over 2, which is supposed to be x over y, is going to give us a over 1. So 0 over 1 is actually 0. It's not undefined. So cotangent of pi over 2 should be 0. Now, why did we get a domain error on the calculator then? Well, here's why. If we go back to what we punched in, we actually have 1 over tangent of pi over 2. So what the calculator does is it first determines what is tangent of pi over 2. And since that returns a domain error because tangent does have an asymptote at pi over 2, it then thinks, well, if I'm getting an error for that, then I can't do 1 divided by error. Right, so that is why we're getting a domain error at this point. So just be very careful about when you're plugging in cotangent values, because those will always have to verify with the unit circle when it comes to multiples of pi over 2. Okay, so remainder of x values, we're just going to trust that the given ones here are correct. So that if I try to check cotangent of 5 pi over 8, that will be approximately negative 0.4142. If I check cotangent of 3 pi over 4, that's going to be approximately negative, or actually exactly negative 1. You can check it on the unit circle. 7 pi over 8. Cotangent of that will give us approximately negative 2.4148. And finally, cotangent of pi, that is going to give us undefined. So you should check this on the unit circle. Okay, basically anything that is 0, pi over 2, or pi, or multiples of those values, check on the unit circle. Okay, so let's plot those, and notice this also has multiples of pi over 8. So I'm going to draw those tick marks before anything. Halfway between 0 and pi over 2, I'll find pi over 4. And then halfway between 0 and pi over 4, I'm going to find a pi over 8. So this is 1 pi over 8, 2 pi over 8, 3 pi over 8. This will be a 4 pi over 8, followed by 5 pi over 8, 6 pi over 8. Okay, so 6 pi over 8, but that reduces to a 3 pi over 4. Then we have a 7 pi over 8, and finally an 8 pi over 8. Okay, so now that those are labeled in, let's plot the points. 0 corresponds to an asymptote. So we'll have an asymptote here at the beginning. Then at pi over 8, we have approximately 2.4. This is 3. This would be 2.5. So 2.4 is going to be right below that line. Then we have pi over 4, which corresponds to 1. 3 pi over 8, which corresponds to approximately 0.4. So it'll be right below that line. Then at pi over 2, we'll have 0. At 5 pi over 8, we'll have negative 0.4, so about there. At 3 pi over 4, we'll have negative 1. At 7 pi over 8, negative 2.4, so about here. And finally, at pi, we'll have another asymptote. So the curve of cotangent looks more or less like this. Now, what if we extend the cotangent graph? If we extend the cotangent graph, we're going to have that same initial curve from 0 to pi. So let's just draw that. And I know that this is at 1 because halfway between 0 and pi over 2 is pi over 4, and we have the point pi over 4 comma 1. This is 3 pi over 4, and 3 pi over 4 corresponded to negative 1. And then we had asymptotes at 0 and pi. So I'm going to approximate the rest of the points so that the curve of cotangent follows more or less what we had on the previous page. Okay, so we're going to have this followed by the same 3 points repeating, but now we have, well, this is 1 pi over 4, this is 2, 3, 4, 5, so 5 pi over 4, 6, 7, 8, 9, this is 10, 11, and 12 pi over 4. Okay, so I'm going to have at 3 pi over 2, you can double check. It's going to correspond to 0. At 5 pi over 4, we're going to get a 1. And at 7 pi over, oh, and this should have been a 4. 7 pi over 4, we're going to get negative 1. Again, I'm just throwing those points at you, but you can always verify by looking at unit circle or by plugging into your calculator. So I'm going to get this curve, and it's just going to repeat. So I've gone ahead and repeated that process in the negative direction, meaning I verified where I have zeros, which happen at multiples of pi over 2, odd multiples of pi over 2, I should say. And I also verified that at negative 3 pi over 4, I get 1, and at negative pi over 4, I get negative 1, that I have asymptote at negative pi, to confirm that this is indeed the curve of cotangent. Okay, so I encourage you to do the same. Make sure that these points agree for cotangent, and then draw the remaining cycles on this graph. We're going to be using them to help us determine the domain. The domain is basically anything that that can be plugged from the x-axis without having any issues. So that'll be from negative infinity to positive infinity, except the places where we have asymptotes, because that is where we'll get something that is undefined. So where do those happen? Well, now they're happening at 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi, basically any multiple of pi. So they happen at n pi, where n is any integer 0, plus or minus 1, plus or minus 2, so on and so forth. What about the range? What y values can we attain? Well, just like in the tangent graph, we can attain any positive y value that we want and any negative y value that we want. There is no break in the continuation of the graph if we're considering going up and down. Okay, so the range will be from negative infinity to positive infinity. For the amplitude, we're going to write NA, because very similar to what we saw with tangent, we have no maximum y value and no minimum y value. That graph extends in both directions forever. And then the period is the place or how long it takes along the x-axis in order for one cycle to repeat, or in order for the graph to repeat. So I can see that one cycle is happening between 0 and pi, and then after that I notice a repetition of the graph. So that means that the period is going to be pi, just like what we saw for tan. Okay, so the period is going to be pi. I'm writing p for the period. Okay, what about zeros? Where does the graph touch the x-axis? Well, that happens at negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, pi over 2, so on and so forth. So the pattern that they all have in common is that they are odd multiples of pi over 2. So the zeros are at odd multiples, so that's 2n plus 1 of pi over 2, so times pi over 2, where n is going to be 0, plus or minus 1, plus or minus 2, so on and so forth. Okay, and finally the asymptotes. The asymptotes are going to be given by whatever we excluded from the domain, which in this case was x is equal to n pi, where n is any integer. That brings us to the final definition that is part of this set of lecture notes, and that is a definition for even and odd. Okay, we're going to say that a function f of x is called odd if f of negative x gives you the same thing as negative 1 times f of x. And it's going to be called even if f of negative x gives you the same thing as just f of x. And for both of these, I want to provide you an example. So for instance, if you take a look at f of x equals, and this is an example, so I'll write e.g. f of x equals x cubed, for instance. Okay. If we take a look at what is f of negative 2, well, f of negative 2 will be a negative 2 cubed, which is negative 8. If I take a look at what is f of 2, I'll get 2 cubed, which is 8. So if I take f of 2 and I multiply it by a negative 1, that's going to give me a negative 8. Right? So if you notice, both of these are the same answer. That means that f of negative 2 is the same thing as negative f of 2. For something that is even, and an example could be like f of x is equal to x squared, In fact, let me make this a little more complicated. Let's make it x squared plus 3. If you check f of, let's say, -2 as well, I'm going to get -2 squared plus 3, which is going to be a 4 plus 3, which is 7. And if you check f of 2, that's going to be a 2 squared plus 3, which is a 4 plus 3, which is also 7. Okay, so they both give the same answer. That means that f of -2 is equal to f of 2. And it's not just a coincidence. If you try it for any other x value, checking f of any negative value will give you the same thing as f of the positive value. And in the case of x cubed, if you check f of any negative value, that'll be the same thing as -1 times f of the positive value. Now, graphically, something very special happens. Graphically, what that means, if I were to graph x cubed, and I'll do it here, it won't be perfect, just so that we can get a rough idea of the behavior. If we plug in a 0, we'll get 0. So there's a point at 0, 0. If we plug in a 1, then we're going to get a 1 cubed, which is 1. If I plug in a 2, so this is 1 and 2. If I plug in a 2, we already saw that that gives us 8. So I don't know if it's going to fit, but we're going to try our best. 2, 3, 4. Okay, let's just make that go in intervals of 2 so that it fits. So this will be a 4, a 2. That just means I'm going to move this point a little lower so that it's a 1, 1. Okay. Then I get a 2, 8. So I get something that looks like that. Okay. If you plug in a 3, you're going to get 27, so it's going to continue to curve upwards. If I go into the negative direction, so this is -1, this is -2, I'll have a -1, -1, so that'll be about here, okay, because this is now -2, and then -4, -6, -8. And then at -2, well, we'll reach -8. So we'll have this curve. So essentially what we're seeing is that this part of the graph that's positive, if you were to rotate it around the x, so using the origin as kind of like a pinwheel, the center of a pinwheel, and you would rotate that pinwheel, you would get that this bottom half of the graph is the same as this part of the graph, but obviously again rotated. And that's going to be true about any function that is odd. If you take that part that is up in the positive direction, it's going to rotate down into across the opposite quadrant, and it's going to rotate in that direction. For the even functions, the graphs will also have a special property. If I graph y equals x squared, I'll get 1, which corresponds to 1. So I'll have that point. And then 2 is going to correspond to 4, right? 2 squared is 4. If I plug in a -1, I'm also going to get 1. And if I plug in a -2, I'm going to get a 4 as well. And then if I plug in a 0, I'll get 0. So it's a parabola. But what's special about this type of graph is that the points reflect across the y-axis. So what I mean by that is that everything on the right-hand side of the y-axis has a mirror image on the left-hand side of the y-axis, right? These points reflect each other. And the same will be true, it's true about x squared, but it's the same is going to be true about any even function, because by definition, If you take the negative value and plug it into f, you'll get the same thing as the positive value. Okay, so these special properties are called, for even, it's called reflection about symmetry about y-axis. And in this case, we say there's symmetry about the origin. Now we want to see whether the functions that we have talked about so far have any type of symmetry, whether it be odd, even, odd or even. So let's bring back one of our graphs. Here is the graph for sine, and the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, does the right-hand side of the graph reflect across to the left-hand side? Well, the answer here is no, right? We don't see that type of symmetry. Okay, so it's not going to be even. The next type of symmetry that we should check for is rotation about the origin, or symmetry about the origin. So if I take, let's say, just like this part of the graph, which is going up in the positive direction, and I rotate it about the origin, am I going to get the same curve? Well, the answer here is yes. If you take a look, focus just on this little piece of the graph. If you rotate it in this direction, it's going to come and lie directly above this portion of the sine graph. So it's actually an odd function. In fact, if you take this whole portion of the graph and you rotate it about the origin, you're going to get, well, this part of the graph. So sine is actually an odd function. So here we're going to select odd, just to test some points and verify that that is indeed the case, because we did it by looking at the graph, but we could also just take some points and verify. If I take, for instance, f of pi over 2, meaning if I plug pi over 2 into sine, well, sine of pi over 2 is going to give me a 1, right? So this is 1. Now if I check what is f of negative pi over 2, meaning if I plug in negative pi over 2 into sine, here's negative pi over 2. For sine, we get a negative 1. So I get negative 1. What we need to check then, is it true that if I take negative of f of pi over 2, that is equal to f of negative pi over 2? Are those two going to be equal? Well, here we're going to get a negative times 1, a negative 1 times 1, and that is equal to negative 1 for f of negative pi over 2. That's a check. So yeah, this even though we've only tested with 1 point, and that doesn't necessarily prove that it's odd in all cases, it does give us a good hint that it might be odd. And then we go and verify by looking again at the symmetry of the graph. Okay, what about for cosine? Well, for cosine, if we look at the graph, for cosine, we said the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, is it true that the right-hand side of the graph reflects across into the left-hand side? And well, the answer here is yes. If you take a look at this part of the curve, it's reflecting directly into this part of the curve. And then the part that's between pi over 2 and pi, we see it reflect here between negative pi over 2 and negative pi. So again, from the graph, we can judge that it is going to be even, but we can just take a look at some points. If I try, for instance, let's say f of pi gives me, or cosine of pi gives me -1. And then if I plug in f of -pi, well, here's -pi. It also gives us -1. So in this case, f of pi indeed equals f of -pi. So we can just, again, it doesn't prove it, but it confirms to us that that cosine is an even function. And we're going to consider one last graph, which is tangent. Okay, here's the graph. And if we focus on reflection about the y-axis, we use the y-axis as a mirror. This part on the right-hand side does not reflect over on the left-hand side, otherwise it would look like a parabola. But if I take this top portion of the graph and reflect it about the origin, I would see that it would lie directly above this portion of the graph. So we have the suspicion, or from the graph, we can pretty much see that it's going to be odd. But again, we can just test some points. Let's try f of pi over 4. Tangent of pi over 4. Tangent of pi over 4 is 1. And now if I try f of -pi over 4, well, tangent of -pi over 4 is -1. So if I take -1 times f of pi over 4, I'm going to get a -1, right? Because we'll have a -1 times 1, which is -1. And that is indeed equal to f of pi over 4. So that means, or that confirms to us that tangent is odd. So these ideas of even or odd are going to be very important for the remainder of the topics that we address in our trig class. So please make sure that you remember these facts and that you also know how to verify their symmetries.